Hello, good morning, good afternoon, good evening, whenever you're watching this. Last time we talked about solving differential equations using that simple mass spring damper system. Today we're going to look at a different way to solve a differential equation using Laplace transforms. Both of these methods are reviewed from your differential equations class, Math 555. So nothing here should be new. You should be going, oh yeah, I remember doing that, and so we're getting you back up to speed on how to do that. All right, so Laplace transforms. First we'll define it, and then I'll show you how we use it to solve differential equations. Basically, a Laplace transform takes a differential equation and turns it into an algebraic equation that's easy to solve, because you go from differential to algebra. We all know how to solve algebraic equations. So the definition of a Laplace transform is you start with a function. In all of our problems, we look at differential equations where the variables change with time, so time's the independent variable. So we're having a function f of t, and you stick that into the Laplace transform formula. So you multiply by e to the minus st and then integrate from 0 to infinity over time. And then you get a function of s, the Laplace variable, that can be real or complex. So time gets integrated out, s becomes the variable, and this maps a time domain function to a Laplace or frequency domain function. Here's an example, actually a couple examples. If we have a function e to the minus at, which we'll actually see a lot when we solve differential equations, you put e to the minus at into the formula, which multiplies by e to the minus st. Combine the two exponentials together. When you integrate, you get 1 over s plus a. With the minus sign, evaluated at the limits. The infinite limit, because of the negative sign, gives 0 for e to the minus infinity. And t equals 0 plugged in gives you this term here. There's e to the 0, we get minus 1 over s plus a. So the Laplace of the function e to the minus at is 1 over s plus a. So the time is gone, replaced by the Laplace variable s. Another example, different kind of time function. This is called the unit step. Because at time t equals 0, it steps up from 0 to 1. There's the unit. So if we plug that into the formula, here's the unit step. It's just 1 over the entire integral, time interval. So integrating e to the minus st, you get minus 1 over s, e to the minus st, evaluated at the limits, and the e to the minus infinity goes away, e to the 0 gives 1, and we end up with 1 over s. So the unit step turns into 1 over s. Another function we'll use, this would model, say, the mass spring damper system being hit by a hammer, as opposed to the unit step where we turn on a force like we did before. So unit impulse is a sudden impulse applied to a system. Mathematically, it's a different kind of function. It's where you have a spike that's infinitely high and 0 in width in the limit. It's defined as, if you take the integral over it, you get an area of 1, because it's infinitely high and 0 width. And the other part of the definition, if you integrate a function f times the delta, the unit impulse, you get f evaluated at 0, which makes sense because the only place f is, or the only place delta is non-zero is right there at the origin. So it picks off the value of f. This is how this function is defined inside an integral. So if we want to take the Laplace transform of the delta function, we plug delta in here. It's directly from this definition above. This picks off the value of e to the minus st at t equals 0. So we get e to the 0 is 1. So the Laplace transform of the impulse is 1. In solving differential equations, we need to know the Laplace transform of a derivative and an nth order derivative. We'll get to those in a minute. Most differential equations have terms multiplied by constants, like we had the mass of 25 times dx squared by dt. So we need to know how to Laplace a number times a function. Well, it turns out that the k just goes along for the ride, and so the k comes outside of the integral. Think about integration, you can always pull a constant out, so you just get the Laplace of the function itself times the constant. If you have two functions added together, think of the integration definition. You can split the integral into two parts, so you just end up with the Laplace of the first function plus the Laplace of the second function. All right, the derivative requires a little more work. We're not going to prove it, but you can look it up in any standard book. The derivative df by dt, if you Laplace it, you get s times the Laplace of f. So it's important to realize that capital F here means the Laplace of little lowercase f of time. And then you get to add on this part here, you subtract off the initial condition, which is the function at time t equals 0. You extend this to a second order derivative down here, and you get s squared times the Laplace of f. And then you get two initial condition terms here. You get s times f of 0 and then f prime of 0. If you think about differential equations, a second order differential equation requires two initial conditions. So that's why these two terms show up when we do a Laplace. On Blackboard, I'm going to upload a handout on Laplace transforms that includes a table of these theorems, and it also includes a table of Laplace transforms. So really, once you've derived a Laplace transform, you don't really do the derivation again, you just look it up in the table, if you remember from your differential equations class. So add this bottom one, which is not in the theorems table in the handout, to your handout, because you'll use it all the time. The key feature here is that if you have one derivative, you get s times f of s. If you have two derivatives, you get s squared times f of s. And if you have an nth order derivative, you get s to the n. So every derivative adds another power of s to the Laplace transform. Sometimes we want to know how to Laplace an integral. So if we have the integral of a function f integrated over a dummy variable tau, then you get the Laplace of f divided by s. All right, so think derivative gives multiplying by s. Integration gives dividing by s. Integration is the opposite of differentiation. Dividing is the opposite of multiplying, and so that even fits together. Another theorem that's helpful is the final value theorem. If you have a function and you want to know what its limit is as time goes to infinity, you don't have to take it all the way to infinity. If you have the Laplace transform version of it, you just multiply by s and take this limit. So the limit of f of t as time gets large is just f of s times s at 0. Okay, so always helps to do an example when we want to solve a differential equation. So let's go back to the mass spring damper differential equation. We're going to plug in our damping and spring and mass values that we used before. The way you solve this differential equation is you Laplace both sides. It makes sense because if you Laplace this side, it's going to be equal to the Laplace of this. And we have to use a bunch of those theorems because we have to know, well, how do you Laplace this thing plus this thing plus this thing? That means you go back to this theorem here that says if you add stuff together, you just Laplace it individually and add it together. And we have to Laplace a number times a function. So we're going to use the other part of the theorem that says a number times a function is just the number times the Laplace. And we need to know how to Laplace derivatives, which we did above. All right, so the second derivative, let's start with this term here. That's actually easier. So we have 25 times x. The Laplace of just the function x turns into capital X of s. That's easy. Okay, the first derivative here, the 12 goes along for the ride. The derivative turns into s times x minus the initial value. Second derivative turns into s squared times x minus s times the initial condition minus the first time derivative evaluated at 0. Again, we're just using the formulas from the theorem up there. For the same example we did before, we're going to say, okay, at time 0, the mass is sitting still at x equals 0, and at time 0, we're going to turn on a force of 25. Notice that we make that happen with this step function that turns on at 0. So it's initially sitting still at rest at 0, turn on a force of 25 at times t equals 0. So that means that these initial condition terms become 0 for this particular example. They are not always 0. If we decided to solve that problem we did earlier, where we pulled the mass over to 1 and then let go, we didn't have a force, but we would have a value here. So I caution you, whenever you solve problems, make sure you put the initial condition terms up here and then plug in whatever values they are to get the correct answer down here. All right, so we get the s squared term, we get 12 times s, 25 times x, and then we're going to leave this general here for just a minute because I want to show you something, and then we'll plug in the 25. All right, so this becomes an algebraic problem, so we simply factor out x and solve. So here's an x, here's an x, there's an x. Factor all those out, we get s squared plus 12s plus 25 times x factored out, divide through, so that goes down here in the denominator. And this is what I wanted to show you. We get the input, that is the force, times this thing, gives us the output response. This is key because this thing in controls and in dynamics is called the transfer function. It transfers the input or the force into the output. That's why it's called a transfer function. And key to this is this denominator polynomial, which you might recognize as being the characteristic polynomial that we got when we used this traditional differential equation solution technique. All right, so the next thing we do down here is we're going to now substitute in for f of s, which is 25 times the step function. The 25 goes along for the ride, and the step function turns into 1 over s. Again, we're just using the theorems that we developed up above from our Laplace Transform tables. So f of s is 25 us of t, Laplace that, you get 25 times 1 over s. So here is the answer. X, the movement of the mass, is this formula. But the problem is it's all in terms of s, not time. Notice that here, again, like I said, here's the characteristic polynomial. Where did this s come from? Well, it came from the input. That's from the 1 over s as the input. All right, so this is the answer, but it's in the Laplace domain. So the next step is we have to inverse Laplace to get back to the time domain. The way we do that is with partial fraction expansion. You're probably saying, oh yeah, I remember doing that in differential equations. And I truly enjoyed it, right? Well, it's kind of a weird technique, but it does work. And what we're really doing is we're saying, okay, I need to figure out what this thing is in the time domain. And the easiest way to do that is to split it up into pieces that I can look up in my Laplace Transform table. So the first thing is to factor the polynomial. And these are those same factors that we got in the solution that we did before. use either your calculator, MATLAB, or the quadratic formula, because this one's the second order, and we get these same roots of the characteristic equation that we had before. So we factor it, and then we're going to say down here that we can write this thing as the sum of factors for each of the terms in the denominator. So we have one for the s, one for the s plus 9.32, and one for the s plus 2.68. Remember, a root with a negative sign ends up in the polynomial with a plus sign, because this is the value that if you stick in for s, you get 0 in that polynomial. All right, so we've got constants up here, k0, k1, and k2 that we don't know yet, because we've got to figure out, well, what do we put up here so that when you add all this up together, you get back to here. Really, it's the reverse process of finding a common denominator. If you said, okay, we've got this stuff on the right-hand side, and we want to add it together, we find a common denominator, that's this denominator here, and then we add all the numerators together. So we're going in reverse, we're going this direction. How do we split this up into the uncommon denominators? But first, let's take the inverse Laplace of this. So here we got k0 over s. 1 over s turns into the unit step. Again, we just look at our table. Here's k1 over s plus 9.32. So this fits the form of s minus a. S plus a. And so the 9.32 goes into the e to the minus at, which is the formula from the Laplace Transform table. Sorry, I drew over this, but the s plus 2.68 goes to e to the minus 2.68t here. How do we find out what these k values are? Well, there's a bunch of different ways. In differential equations, you probably multiplied both sides by the entire denominator and then equated equal powers of s, and I'll show you an example of that later on in part 2 of this lecture. A quick way, if you have individual factors like this with no repeated denominators, is to find this, k0, we multiply both sides by s and set s equal to 0. It's a little faint here, I hope you can see it. So you multiply both sides by the denominator. So what that does is it gives us an s times this stuff over here. The s cancels out here and cancels out here. So what does that give us? Well, it means that when you set s equal to 0, it knocks out all of that stuff. And you're left with k0 all by itself over here. And then when you stick s equals 0 in over here, you plug it in for s here, and it gives you a nice, easy formula to calculate for k0. How do you get this one here? Multiply both sides by the denominator and evaluate at the root. So we multiply by this, and then we set s equal to minus 9.32. How does that work? Okay, we multiplied both sides, so cancels out here. So we just get k1 by itself, cancels out the term over here on the left, and then when we set s equal to minus 9.32, this gets knocked out, so it knocks out all of these terms on the right except for k1. And when we evaluate, we get this value for k1. Same process. For the next root, let's go up here, s plus 2.68, multiply both sides by s plus 2.68. So you get this times this, cancels here, cancels over here. Evaluate at minus 2.68, because then that's going to knock this term out. You get k2 all by itself, and you can calculate it as minus 1.404. So plug k0 in here, k1 here, k2 here, and now we can look these up. Well, we already did that. We can look these up each individually in the Laplace table. So we inverse using the tables on each individual part, and we get 1.404 minus 1.404 times the time domain functions. All right, almost ready to wrap up this lecture. The last thing I want to point out is the names of what these parts are called. This part is called the transient solution, because as time gets large, these e to the minus t terms go to 0. So this term, this part of the solution goes to 0 as time gets large. And this one sticks around. So this is called the transient solution, and this is called the steady state, which means as time gets large, this just sticks around. In differential equations, this corresponds to the homogeneous solution, and this corresponds to the particular solution. Or you can call it the unforced solution and the forced response, because this thing showed up because we had the 1 over s that came from the f of s being 25 over s. Okay, last thing I want to point to is look at the eigenvalues, which are the roots of the characteristic polynomial. This is the minus 9.32 and minus 2.68 that were the roots of that s squared plus, what was it, 12s plus 25. Yeah, well, here we go. It's right here. Those are the roots of this thing. And look where they show up. They show up here in this solution term and here, because each of those individual factors of the polynomial up here were what led to that part of the solution. We factored it. Here's the roots of the polynomial. They go into these terms here. Why is that important? It's because we can actually look at the signs on these and determine whether our system is stable or not. Because we had a negative sign here and the root was negative, right? There's our root, shows up here. Because both of these roots were negative, the transient solution went to 0 as time got large, and we were left with a steady state solution. That's a definition of dynamic stability, is that this thing damps out. What if we had one positive root? Only one. Let's say that the sign on this was plus rather than minus. This still goes to 0 as time gets large, but this is going to blow up. It's going to go to infinity. And so that's an example of an unstable system. So we can actually define stability, which we'll do in part 2 of this lecture down below. We'll look at the roots of the characteristic polynomial, and they will immediately tell us what the response looks like. What if the roots are complex? We had real roots, but you know polynomials can have complex roots. That we're going to do in part 2, along with some other different situations. All right, so this part 1 of the lecture is done. And part 2 will continue on with some more to do with Laplace transforms.